Heun equation is the differential equation, and I think almost all of you use differential equation. So of course, as you know, differential equation is important, and yeah, so in that sense, differential equation, I think differential equation is a common language, I think. And today I focus on the second order linear ordinary differential equation, which is something like this type. So yeah, second order and linear differential equation. This one, and then we can further classify this equation by considering counting the number of linear points on functions p and q, coefficients p and q. For example, when the number of singularity 1, which is the typical equation is like this. Or it looks that this differential equation doesn't have a pole, but when you go to infinity by changing coordinate, for example, then by changing coordinate like this, then you can omega equals 0 responds to the infinity. And then after short calculation, you can just find that the differential equation becomes like this. So now we have a pole at that equals 0. So anyway, this type of this differential equation has a pole, one pole at infinity. And you can also easily find that the solution like this. So it's simple. Then what happens when the number of poles is 2? In that case, typical differential equation, typical form is something like this. And in this case, one can also find a solution, something like this. So so we can write down solution in terms of fundamental functions. So it's still simple in this sense. Okay, next 3 case. Then actually the situation drastically changed, and we can't write general solutions in terms of fundamental functions. And now it is known that the solution is the solution is called hypergeometric function. It's like this. And in the previous century, this case, or this hypergeometric function was studied. So the next step is hope. Then at least in this case, the solution is called point function. So point function actually, and actually in this sense, point function or point equation is differential equation in this century. And actually, for example, in Mathematica, the point function was implemented in 2020. So it's very recent, right? So actually this point function is the frontier of this type. note that the form of point equation is something like this. Yeah, although I don't, I mean, yeah, I just showed it. You don't have to remember the detail. Yeah, but anyway, yeah, this equation is now important. And okay, then we move to the black hole physics. And yeah, I will explain why. Yeah, I mean, actually, the point equation appears in black hole physics. So why? Okay, let us consider the black hole merger. So yeah, this means that in the first step, we have two black holes, and then they merge, and then finally they become a single black hole. And yeah, in this, I mean, very interesting phenomena, the gravitational wave is appears, and the typical form of gravitational wave is something like this. In the first step, we have this amplitude and the merged big amplitude. And then in a final step, it's an upside. I mean, it behaves as an exponential dump with oscillation. So if you write, yeah, and note that yeah, actually this gravitational wave observations are underway. So yeah, actually this is also the frontier in gravity physics, black hole physics. And yeah, let us focus on this part. Then yeah, as I said, yeah, I mean, the function can be written something like this: exponential I omega tau is time, and yeah, and this omega has a real part and imaginary part. Of course, real part is the oscillation, dominates the oscillation, and the imaginary part dominates the exponential term. And yeah, so anyway, so I mean, in theoretical physics for the black hole, it is important to find the omega as a function of the station of the black hole, something like mass or charge or angular momentum. Yeah, so anyway, we want to calculate this omega, and this is called quasinormal mode QNM. So yeah, anyway, we want to compute this. So how to compute? Of course, we are considering the gravitational wave, or I mean, so gravity. So this wave must satisfy the Einstein equation. And but yeah, Einstein equation itself is very difficult. But I mean, as the first step, let us consider the linear. I mean, let us linearize the Einstein equation. Then actually in this black hole case, point equation appears. So in this sense, I mean, omega, the quasinormal mode is determined by solving the point equation. And with the quasinormal mode boundary condition. So yeah, I mean, yeah, as I told, point equation appears, but let us go a bit in detail. So we have to impose the boundary condition like this. So here we have there is a black hole, and also we observe far from here, and This is physical situation. And then the boundary condition is such that, okay, so yeah, because this is wave, we have I mean waves ingoing in this case ingoing phase and outgoing wave and outgoing wave on both boundaries. And because we want to consider the quasinormal mode, or I mean this last step, and in this last step, no energy will be provided to here. So we want to consider the case when we don't have this wave and this wave. We only have this one, this wave. Yeah, so this is the physical boundary condition. But then what do you mean in this boundary condition in terms of point function? Actually, in terms of point function, first, here and here is a pose. This 2 of 4 poles. And these two waves are two independent solutions, and this pole and this pole respectively. So in that sense, in terms of point function, we want to know how they, I mean, two solutions around different poles are related to each other. And so that, if we know, then we can impose this boundary condition. And then by solving that equation, we obtain the quasinormal. But I mean, it's a hard problem. No, I mean, exact form is no. But no one knows the exact form. But then gauge theory appears. And because we don't have that much time, I drastically should I don't go to detail, but anyway, very very roughly speaking, so let us two-dimensional conformal field theory, and we can consider coordination functions, which is fundamental observables in the conformal field theory. And one very important point is that I mean, they are actually the solutions of, it's known that they are the solutions of point functions. And also in this case, because this z, that is I think the variable of the differential equation. And in this case, z is near t. So this can be interpreted as a solution of point equation near this t. And in this case, because z is near 1, the position is changed. So this function can be interpreted as a solution near z equal t, z equal 1. And another important point and very strong result is that the relation between these two correlation functions can be written in terms of free energy of four-dimensional gauge theory. So this is, I mean, yeah, quite different from this 2D shifting. Yeah. And yeah, so this is also miracle. But yeah, and then this is just a remark that yeah, this I mean there is a correspondence, miracle correspondence for the AGP correspondence, and yeah, this relates to the safety and for the case theory. And by using this, we can write down the relation in terms of the free energy for the case. Yeah, so yeah, this is why black hole physics needs the gauge theory. So yeah, finally, I want to comment on the Heun equation in this. Actually, I asked this in to the chat GPT and yeah, so I completely don't know about this, so I want to comment. Okay, so the first example is population genetics, and yeah, he said that selection here, I think he or she selection and mutation and genetic drift, and I mean setting set up this and then consider the Fokker-Planck equation, then the point is point function here. Or another example is quantum optics. When we consider two-level system, two-level energy system, and add photon modes, one photon mode, then the eigenvalue problem, yeah, again reduces to the point function. So yeah, but I can't forget it. So and okay, almost finished. But I just want to comment that I think we will have Hatsuda-san's talk here on second week. Yeah, anyway, on September, and I think he will put about something which is closely.
That one is a different.
Yes. Yeah, so yeah, if you are interested, yeah, I mean, I actually started the recipe. Yeah, in his book. So yeah, anyway, thank you.
So we accept the question from the experts, especially So does anybody know when the Heun equation appears in population genetics? Nobody. Well, okay. So any question? Yeah.
What is your underlying space of your OD?
So ordinary differential equation.
What is the underlying space of this equation?
Underlying ordinary.
Yeah, yes. This equation.
I think this means.
No. What is the y? Where's y lives?
Why?
Yeah. So this variable is in the element of R3 or Sn.
I mean, Riemann surface.
Riemann surface. Okay.
With infinity.
What is it? Okay.
Yeah, I think.
Reject this.
Yeah.
Isomorphic to S2. That's
Yeah.
the fear.
Yeah.
Yeah.
What is the special of the Heun function? It is just 2f1.
So number of both are different.
Yeah, it's just one of the special functions. What is special in Heun function?
When function itself. But I'm not sure this is.
Maybe the question is how it is different from the ordinary hypergeometric function.
Yeah. So I'm not sure whether this what I will say is what you want, but I mean the big difference of the equation between this and this type is that I mean we have degrees of freedom of changing coordinate, and so that for example for this case we put 3 force at for example 0, 1, infinity. But in this case, we must have free. I mean, there must have here the moving pole, and I think it drastically changes or makes it difficult to study the differential equations. So it is okay.
So I guess this is a very naive question, but you mentioned there's like 0, 1, 2, 3, or 4 solutions. So is it possible to have like 5 or like more than that for like is this gonna be the 22nd century or is that
Yeah, I hope so. But and I don't know about much about it.
but not theoretically possible?
Yeah. And in that case, we have more moving force, and it must be more difficult.
Thanks.
Okay. About quasinormal mode. So you assume that QMM boundary condition. So how reliable it is, or can we use it as a null hypothesis? So how that assumption is valid valid for real observation now.
So keep on now. Killing them.
So you
Yeah,
first quasinormal mode, right?
Okay. I think I mean okay. There is there are some papers. It compares observation and I mean this could be a little more and they fit well actually. So
Yeah, so the black hole absorbs energy or everything. Because of that, if we impose some boundary conditions at the horizon and at infinity, then it's written right here. This frequency has an imaginary part, and this imaginary part means where black hole absorbs energy. So that's why this is very important.
But still, so due to the change of the shape itself, so I imagine that many different frequency will appear.
Yeah. Of course. I mean, this is I mean, first. What to say? But anyway, of course, we have many modes.
Okay, right.
Yeah, and yes.
Yeah, so the information maybe the gravitational wave data where we can explain and
Okay.
I have 2 questions. One is when you write down the Einstein equation for this 2 black hole rotating system, do you exactly get this Heun equation?
No.
Precisely, you get this.
Actually, what we are doing.
That's what you're claiming.
I mean, at least we have to linearize the Einstein equation
No,
around the black hole.
linearize it, okay, but you get this equation. Exactly.
After changing.
Exactly, you get this.
Yes.
Well, not right.
I mean, after changing the coordinate appropriately.
So you have a paper on this.
Yes.
Well, anybody else solve this, got this solution?
Yeah, yeah.
Exactly.
It's yeah, this comes from Polsky equation.
Linear is okay. But exactly this.
Yeah, yeah. After linear,
Z minus one.
In this asymptotic region.
Yeah, asymptotically you get that.
Yeah, yeah, yeah.
Another question is gauge theory versus conformal field theory. I don't know any exact precise proof.
No, no, no.
I recently proved the anti-de versus conformal theory. Exactly. But I don't know any other proof. And are you claiming gauge theory, for example, four-dimensional SU3 versus two-dimensional conformal theory? Can you prove it? Exactly.
Yes, it is. But anyway, no, no. In my understanding, this is the conjecture. But
It's just a conjecture.
yeah, but currently we have many observations that I mean,
You
physical
can't
quality-
prove it.
yeah,
Okay.
yeah, yeah.
So let's see. So in the case of hypergeometric function, one of the interesting features is to consider the monodromy of the solutions. There is a Stokes phenomenon. Now, in the case of Heun equation, there is a moving singularity. So I would imagine that there is a parameter-dependent monodromy, and I wonder whether there is any physics phenomena corresponding to that in any of the physical systems for the monodromy.
But for example, we can consider right monodromy deformation, which
Yes.
claims that I mean, even if we move T, the
Okay.
monodromy is different.
Yeah. Okay. I see. So
Well,
maybe this was monodromy, but
Yeah.
I see. Then the question is like, what physics does the monodromy data encode? Do you have any idea? Like, typically go around the parameter. Yeah, for example, in fact, in the case of conformal field theory, in some context, that represents the chaotic behavior of CFT, for example.
Oh, yeah.
Yeah,
sorry,
for example, so yeah, so I wonder whether there is a similar phenomenon in, for example, more in the black hole context.
Yeah, but for
Maybe that question is related to Morikawa-san's question, why this equation is important in this context.
yeah, sorry, I don't know about it. I can't answer it. Question about black hole. So, but yeah. Yeah, sorry.
Well, yeah, okay, it's already an expert question, but any non-expert question?
So maybe it's not a question or a comment for the biology part. So I think.
Oh, you have an answer.
No, I don't know if it's an answer. I think there is a paper on archive that links like population genetics and functions. So I guess that ChatGPT was looking at that. So I think it's more property of the, if I understand correctly, it's more property of the Fokker-Planck equation. So if the basic population genetics model is a Fokker-Planck equation, and if you want to solve the Fokker-Planck equation, or at least that particular form, you look for eigenfunctions of the equation, and the eigenfunctions are solution of an equation after a few transformations. So I think it's more property of the Fokker-Planck equation than anything related to population genetics. Just a comment.
Oh, and in which case this equation appears?
The Fokker-Planck equation.
Well, no. Fokker-Planck equation always appears, but it's a point equation with four singularities. So is that a very special Fokker-Planck equation? Well,
I think
yeah, I thought the question to you, but
This genetics only requires hypergeometric function.
oh, yeah.
I think
Yes.
in this data, these are the condition.
That is called genetic term, yes, but
Genetic term.
term itself is already considered in hypergeometric function solution. Yes.
And Yeah, yeah.
So,
So it's a generalization of some additional term is included, or that kind of modification
Yeah,
is
yes, it's not typical, I think.
Yeah, 1, 3.
And so in the word selection can contain any kinds of function. So so we can consider the special case. It's falls into have this kind of
point.
yes. But we must check if it's realistic or not. Yes.
Yeah, thanks for the comment.
Yeah. Thank you. Further questions? Well, expert. Questions fine. Oh, okay.
Yeah, just have one comment and one question. So the comment is about the previous question on boundary conditions. So there's a very physical reason for posing the boundary condition. So you know the black hole and the observer are very far away from each other, and observer is we assume that the observer is a symptotically flat region, and so we, as an observer, we receive gravitational waves. We don't expect any other things shooting toward the black hole, so that's why we are purely all going on there. But event horizon, I mean, the other boundary condition is on the horizon. And event horizon is boundary where nothing can escape. So precisely the reason why we have only ingoing boundary. And then people use these boundary conditions to compute quasinormals, and they match well with observations. So that's the reason. And the question is more an open question right now, like specifically why is Einstein gravity so spatial in the sense that if you linearize on the Einstein equation and then perturb curve geometry, you get point equation, as you say. But if you slightly go beyond general relativity, this property it's not valid anymore. So do you have any idea or any
So do you mean more general solution?
modified gravity? I mean, by considering modified gravity or by considering other geometry, other types of black hole different from curve. And I believe, I mean, this point equation it's not working anymore. So in this sense, this setup is very natural and also very spatial. So my question is like, do you have any idea like how to explain this, or for example, from gauge theory point of view?
Yeah, okay. So first of all, I don't know the overview of this field because I didn't this time. So, but in my understanding, actually for more general case, for example, for more general solutions, point equation, or in other words, singular point, four singular point case also appear, and they are also studied. But I mean, so yeah, so in other words, the research is, I mean, but research is bounded by the number of singular points.
Well, yeah, so this point equation will appears as a linearized Einstein equation around the curved black hole with angular momentum or without charged black hole.
Yeah, both we can.
So even the black hole has an angular momentum. Well, so in that case, this point equation here.
Yeah.
Oh, I so
for more, more general case.
oh, I
Also I don't know.
So of course maybe there's no charge but only mass and angular momentum. In that case, so this point equation.
Yeah, charge can be also considered.
Okay.
Charge.
Oh, even if there is a charge,
Yes.
where the linearized equation becomes point equation.
Yeah.
Okay. But you mentioned that too. I forgot the name, but some very complicated equation starting with T. Yeah. I think that the equation is a linearized equation around the curve solution without the charge.
Without charge.
Yeah.
Yeah, but so anyway, my co-author
Oh,
provided me the yeah communication with the
oh,
church. So
oh, I see. Oh, then,
yeah, I must ask him. But maybe my understanding. Maybe.
How about the case of the neutron star collision? Can you expect similar equation?
But I don't know about that. But yeah, it must be interesting.
But in the case of neutrons, I think that there is no horizon. So we cannot impose such a very strong conditions event horizon. So
Yes.
I guess yeah, the normal quasi-mode is more complicated.
Yeah. This pole is related to the horizon of the core actually. Yeah. So perhaps it reduces to simpler case. At least in the yeah, infinity of small horizon, we have some pole. So but yeah, and yeah, if polar horizon vanishes, then it's the equation must be this simpler case.
So does the cosmological constant change the situation?
Yeah, actually, that's a very interesting question of what we are studying now.
You were studying now.
Yeah. And we are considering Cardo-Zeta case and taking the flat limit. And anyway, I can say that for both cases, pointation here.
Oh,
Yeah. You cannot cosmological constant or just set it to zero.
then what are you studying then?
Yeah, by taking the limit.
The consistency between the flat limit and exactly flat case.
Yeah.
See.
Yeah, I'm computing that in the flat limit. No. Yeah. Sorry.
Okay. Any questions from online participants? No. No further questions. Okay. Okay. So thank you very much.